Hope everyone's having a good week so far. It's 8:30, so let's go ahead and dive into day 7. Well, first we'll wrap up the remaining discussion at the end of day 6, and then we'll jump into day 7, where the focus will be metal carbines, as well as other metal multiple bonding complexes, how to make them, how they react, and how to understand structure and bonding. Before getting to that, I wanted to conclude our discussion of elementary steps. Is everyone able to see this screen share, my iPad? Okay. So we left off on 1-2 migratory insertion, and there are just 2 relatively brief sections remaining here to get through. Beta hydride elimination and transmediation. So let's go ahead and wrap that up. So we had talked about some of the general properties of 1-2 migratory insertion, how it's typically favored for metal H as opposed to metal alkyl, metal H or metal aryl as opposed to metal alkyl, although metal alkyl is still possible. And this reactivity trend is a little bit different than what we saw in terms of migratory aptitude into CO groups in 1-1 migratory insertion. And we talked about 1-2 migratory insertion being predominantly, reactivity trends being predominantly determined by kinetics and thinking about the transition state and which is more hindered or less hindered, and CO migratory insertion often being determined by ground state stabilization or destabilization and the underlying thermodynamics. So let's now illustrate this elementary step of 1-2 migratory insertion with a specific example. So let's consider this zirconium bis CP methyl complex and a reaction with, so I have a free coordination site drawn here, and then reaction with ethylene. So let's go ahead and walk through what's going to happen in this sequence. Nathan, are you there?
Yeah.
Okay. So first step.
Would you have the ethylene coordinate to the zirconium?
Okay, very good. And what next?
Could it do migratory insertion on the methyl group into the alkene?
Yep, so Nathan is rightfully noting here that we had just talked about reactivity trends, that hydride's going to migrate first and then aryl and then alkyl. But in this case, what is there? You have only CPs, and those, as we've already covered, are typically spectator ligands. And then we have a methyl. So it's going to be, the methyl is kind of our only choice here. Okay, and so from this, Nathan, we get a what's the product going to be?
It's like a propo alkyl ligand with an empty side.
Okay. And I had mentioned that, I didn't mention this, but this is actually under an atmosphere of ethylene. So what would you expect might happen next then?
Oh, is it like a polymerization process?
Yep, very good. So now you're free to coordinate another molecule of ethylene. And as Nathan said, this will go on to oligomerize or polymerize. And in this case, it will, the product will be polyethylene. And this process is, I guess the polyethylene polymerization specifically would be the Ziegler process, but in general, this process is called Ziegler-Natta polymerization, which won the Nobel Prize for both of these scientists. Natta's contribution was predominantly in polypropylene, polymerization. And this reaction, particularly in its heyday in the mid 20th century, I think or mid to late 20th century was around 100 million ton scale, and originally discovered at the Max Planck Institute for Kohlenforschung in Mulheim, and these patents there are very valuable and a source of continuing financial strength for that organization. Okay, any questions on that? This is a relatively simple, it's an industrially relevant real world example, but one in which it's mechanistically fairly straightforward because you only have a limited number of options for each elementary step. We'll see examples that are more complicated as we move forward in the class. So now let's consider the microscopic reverse of 1,2 migratory insertion, which is, in general, we would call this beta elimination, and where this is most common is in beta hydride elimination. And so this process takes place rapidly. It's an intramolecular elementary step, and thus is quite rapid, provided that there is an open coordination site on the metal to form this agostic interaction that we were speaking of, and I've shown the transition state here. So first the formation of the agostic interaction, and then a transition state of a four-membered nature as drawn. So if you want to suppress beta hydride elimination, then you would want to have a trapping ligand and so maintaining coordinative saturation post migratory insertion. So typically, like as we'll see in a Heck type process, you'll have an aryl metal migratory insertion, and then you would have beta hydride elimination. A way to prevent beta hydride elimination would be to maintain coordinative saturation. Okay, let me open my blinds here so I don't look like I'm sitting in a closet. And then in terms of relative rates and reactivity trends, beta hydride elimination is significantly faster and more common than beta alkyl elimination. There's another process that you may encounter during your research, which is beta heteroatom elimination. And this, depending on the system, can be competitive with beta hydride elimination. So if I had to put a general rank order, I would put beta hydride elimination, beta heteroatom elimination, and then beta carbon or beta aryl elimination. Okay, let's go through example here. Okay, and maybe we'll take a volunteer. Anyone want to walk us through this? I guess first the name of this reagent, and then
Schwartz.
how to make it. Okay, was that Tim?
Yeah, and you make it from the dichloride and reduce.
Okay, and what would be a reducing agent?
I don't know if lithium borohydride is strong enough, but probably like aluminum hydride.
Okay, LAH. Good. In reality, this LAH reduction actually gives a mixture of typically gives a mixture of the monohydride, which is Schwartz reagent, and the dihydride. And then the dihydride, if desired, can be converted to the monohydride just by adding DCM. Okay, Tim, let's take us a couple steps further here. So I've drawn this association step. Oops. And what's going to happen next?
I have 1,2 migratory insertion,
Okay.
forming a between the H and the alkene.
Okay. So I'll draw where the H, well, maybe I'll draw that on the same side just so that's crystal clear. Okay, and then is this happy as is, Tim, or can anything else happen?
I don't know if you're adding more of your dyeing. If you're adding more, you might just do the same process that Nathan walked us through. But if not, then would you get beta hydride elimination from the terminal methyl group?
Okay, and why would you say the terminal?
Sterics.
Okay. Oops, sorry about that. So we're going to have a bond rotation here. Maybe I'll just draw that so it's totally clear in case anyone is confused. We have the bond rotation. I think this is a fairly common theme in beta hydride elimination processes that you typically need some rotation. 1, 2, 3, 4. Okay. And then you said you were going to beta hydride eliminate to the methyl. And then we'll have the terminal alkene complex. And then are we done? Tim?
I think, sorry, yeah, I think that alkene can fall off and maybe another one can come in. I think that would be.
What else could happen from this intermediate drawing?
You go back to one of the intermediates that you drew earlier.
Okay, yeah, all of these steps in principle are reversible. Is there any step that we haven't already shown?
I guess, could you, well, maybe you could also do another 1,2 migratory insertion
Okay.
to form the secondary alkyl zirconium bond.
Okay, what about this other possibility? Where you do, as you said, another migratory insertion, but in this case, you go the opposite way around that you had, or I guess, depending on your perspective, you go along the same direction of the chain to get to this primary alkyl intermediate. So now this is primary. And as a general rule of thumb, primary alkyl metal species are more thermodynamically stable because they're less crowded than our secondary. So there's a thermodynamic driving force for this metal to walk down the alkyl chain, and this is a process called chain walking. Super, Tim. Thank you. Any questions on that? So let's see these reactivity principles now play out in a more modern well, arguably more modern example, although this application of Schwartz reagent is still quite useful to this day. So let's now turn to problem of the day number 3 from last time. I have it sketched up here, but let me, if I can manage to not cause a disaster here by doing a new share, show you the whole system. So we have a reaction where we are taking a secondary alkyl bromide in the presence of nickel, in the presence of manganese as reductant, and presence of CO2, and getting to this linear product. And key here is this specially designed phenanthroline or derivative with bulky substituents flanking the sp2 nitrogens. Okay, so let's now go back to the other screen and discuss a mechanism for product formation. And this will help kind of usher in our discussion of catalysis, which will be a big focus moving forward. Okay, Noor, what do you expect might happen in this system?
Well, you'd have the same chain walking concept to get to the prime.
How does it get started in this case? I guess that would be the difference.
All right, so you'd have oxidative addition.
Okay.
And then you'd have beta hydride elimination. Either side can happen, but then that should funnel down to, well, that's reversible essentially through 1,2 migratory insertion. And then you should finally end up with the primary alkyl anion through chain walking.
Okay. Let's just back up quickly. How did you expect this oxidative addition step to take place, first off?
I mean, considering that it's nickel, I want to say radical.
Okay. Yeah, I think that's good thinking. You've got a first row metal, you've got a secondary alkyl halide, which we saw are generally signaling element. Both are generally signaling elements for a radical pathway. The oxidation state of the pre-catalyst here is nickel +2, but we see that we have reductant present. So presumably this is going to get reduced down to either nickel 1 or maybe nickel 0. If you drew either based on the information provided, you wouldn't necessarily be wrong. But I think the authors draw this as nickel 0. So let's go ahead and draw out this, as Noor said, a radical-based pathway. So we get homolysis of this carbon halogen bond. I'm just going to draw this like this. Now we have nickel 1 bromide. Recombination, as Noor said, that gets us to a nickel 2 alkyl. Now there's some potential subtlety here that I don't necessarily expect you to have totally thought through, but with manganese as reductant, at which stage, and we know this is overall a reductive process, at which stage does nickel get reduced down? Do you reduce it down now? Do you reduce it down later? Let's not focus on those details. What Noor said next is that, just analogous to what we saw before, we're going to have a chain walking, so beta hydride elimination to generate an alkene bound nickel hydride and reinsertion. I won't draw that out. It's the same as we saw before. So I'll just abbreviate that with this multiple arrow to get to eventually the primary, as Noor said, funneling through thermodynamic control. And then the last step is going to be trapping with CO2.
What would you need to do to favor kinetic conditions?
Well, what do you mean by kinetic conditions, Tim?
Let's chain walk in the other direction.
Okay, let me draw this out and then I can respond to your question. And then to close the catalytic cycle, because we did ask you to think about how you would turn this over. This is a pretty unappealing looking catalytic cycle. So sorry about that. You'd need to reduce with manganese. And again, based on the information provided, don't worry about what order the reduction happens as opposed to other steps. So Tim was asking a good question, which is how do you favor kinetic control in such a process? And there are two layers to that. The first would be, let's say maybe you want kinetic control, and the type of kinetic control you want is a non-chain walking process. And you want it to couple selectively at the secondary alkyl. And we could go back to these principles we talked about, where we need to have ligands then that are, let's say, tridentate, so you don't have an open coordination site to form the agostic interaction and route to beta hydride elimination. Or you need coupling partners that react sufficiently fast that bimolecular coupling is faster than unimolecular beta hydride elimination. The other question is a more challenging and arguably more interesting, and actually one we've been thinking about in our group, which is how would you trick the system into chain walk in the opposite direction and walk into a position it doesn't want to walk in. And so there are different strategies people have thought about. You can put what are called like redox terminating groups. Larock has really pioneered this, as well as more recently Matt Sigman in the context of palladium. We've been thinking about chelation controlled chain walking processes in our group, as have others. So yeah, interesting question, Tim. Okay, good. Any questions on that?
I have a quick question.
Sure.
Would the bromide fall off, or would you go through the pentavalent, like the 5-coordinate system, to do the beta hydride?
Oh, you're asking about this step, Noor?
Yeah.
I think in principle, either way around can happen. I'd have to look at what the authors draw for this.
Okay.
But like either way, I think carbon halogen or a nickel halide ligand exchange should be relatively facile under the reaction conditions. So you can open up a coordination site that way as needed. I guess.
Yeah, I think you can also reduce this intermediate to nickel 1 alkyl, which is what they propose in some of their papers.
Right, yeah, so the timing, there are two single electron transfer reductions that need to happen. The timing of when they happen is subject of much debate in this area. And so I sort of glossed over some of those details, but yeah, thanks, Tanner. Okay, let's now continue charging forward to talk about our last elementary step that we'll focus on before concluding this part of the class, but we'll continue to come back to these and provide more in-depth discussion as we see more real-world examples. So transmetallation is a critical elementary step for one of the most widely used organometallic reactions around the world, which is cross couplings. We already covered this if we think back to our discussion of main group organometallics. So we won't rehash all of those details, every different type and subtype of transmetallation, but I did want to highlight particularly the types of transmetallation that are most relevant to cross coupling, and that's really this bottom type here. So I've restated some types of transmetallation that we've already covered. Transmetallation between two organometallic. Oh, sorry, I guess these two. Let me make sure I have this right. Yeah, this is what we'll see, I guess, as being most relevant for cross-coupling. So you can transmetallate between two organometallic reagents. You can have this sort of so-called redox transmetallation, where you have a metallic form, zero oxidation state form of a metal, and then you get transmetallation with concomitant redox adjustment, and then transmetallation between an organometallic and a metal X, which is a common theme that we'll see in cross couplings. So just like before, these reactions, the underlying thermodynamic driving force for transmetallations ultimately stems from the underlying electronegativities of the two metals that are involved, and the as stated here. Let me make sure I have this right. When there's a strong thermodynamic driving force is when the metal 2, I mean, there are two ways to look at this. When the metal 2 is more electronegative, because then it's accepting the R group, or the other way to look at it is when the metal 1 group is accepting, which is more electropositive metal, is accepting the X, which is itself a more electronegative group. So in general, the thermodynamic driving forces, you want to pair electropositive and electronegative. As I just stated, this is a constituent elementary step in cross couplings. There are all sorts of flavors of cross coupling. We have a separate lecture on cross coupling, so I won't get too much into the weeds here. Basically, depending on the organometallic nucleophile that's used, each of these has a different name. They're all name reactions: Suzuki, Yama, Denmark, Stille, Negishi, Kumada, and each of these different organometallic reagents has a different inherent rate of transmetallation, and then inherent challenges or opportunities associated with their use. And to summarize quite a lot of work, transmetallation is complex and it mechanistically, and it depends on a number of factors: the metals that are involved, the groups that are being transmetallated. So there are a couple of points that I want to make today, and most of the discussion will focus on, I guess, the two that I think are fall most outside of the scope of what we already covered. So these are the least like the types of metals we talked about in main group organometallic, and also two of the most widely used in synthesis, which are organotins and organoborons. So first, one area of research I think that has been really come online significantly, let's say in the past decade. I think this wasn't even really, I can't even remember learning about this when I took organometallics, and I'm sort of dating myself here, about the stereochemistry of transmetallation. And so the reason this has become an important area of study is now it's relatively straightforward to access enantioenriched chiral secondary alkyl boron compounds, for example. And now there are a growing number of metal ligand combinations that enable these to act as cross-coupling partners. Thus, people have been able to interrogate systematically what are the stereochemical outcomes when you go with an enantioenriched sp2 organometallic. Is it stereoinvertive? Is it stereoretentive? It turns out that actually both pathways can be operative. So the simplest case is just when you have an CSP or CSP2 hybridized carbogenic group, and in that case the systems are stereoretentive. So think here like alkenyl, and I think we all know this intuitively. Alkenyl tin reagents or alkenyl boron reagents. Those are stereoretentive in terms of the alkene geometry. sp3, it's more complex. So you have two different pathways. One, which is called an open or acyclic pathway that is stereoinvertive at the carbon atom. And the other, which is called closed or cyclic, is stereoretentive at the carbon atom. And this has been reviewed and highlighted in several prominent examples. I think, to me, like, the closed version is pretty intuitive to think about, whereas the open, I always sort of honestly scratching my head left thinking, like, how does this work and what are the orbitals even involved? But you can think of it vaguely as being analogous to sort of an SN2 type oxidative addition process, if that's helpful. And if it's not helpful, then pretend I didn't say that. Okay, let's look at a specific example of an open pathway, and this one I had to draw in advance because I didn't want you to spend. I didn't want to embarrass myself for 30 minutes as I tried to draw what this transition state looked like. So here's an example from our chemist of the day from last time. I don't know if anybody recognized him from the photo or from the chemistry. I think we actually covered one of his, if not this paper, one of his papers in group meeting. Let me quickly reshare. Oh, well, I almost left group meeting. Left the meeting. That would have been very bad. Okay, any takers? So this is a example from Seung-Hwan Cho's group. He did his BS and PhD at KAIST, the latter under Sukbak Chung, and then postdoc with John Hartwig at Berkeley, and since 2014 has been working as an independent investigator at POSTECH, which is in Pohang in Korea. I like this example because it's something I think kind of unusual, which is you have these geminal di organometallics, in this case geminal 1,1 bisporal compounds, and the transmetallation event has the opportunity to control stereochemistry in the product. So first, let's draw out what the product might be for this. I'll ask someone to volunteer. Daniel, what would you think a reasonable product for this reaction might be?
So I think the carbon bound to the bromine would end up being bound to the would end up forming a bond between the carbon we see in that transition state. That would be my guess.
Okay, let's see if I can get this right. So this type of product, Daniel? So the newly formed bond is this one?
Yes, yeah. Sorry, I thought you were asking for like a type of like name of this product. I wasn't.
Oh yeah, I guess it'd be a homoal boron compound or something. But yeah, perfect. So it's basically, you can think of it as kind of like a Suzuki coupling, essentially, between an al electrophile and a 1,1 bis boron. And the cool thing is that you have these two organometallic groups, and the transmetallation actually has the opportunity, the catalyst has the opportunity to pick one or the other to establish stereochemistry, which I think is a really unusual means of controlling the stereochemical course of a reaction. So Sung-Hwan Cho has worked actively with these 1,1. He's not the only one, but he's worked actively with new ways to generate 1,1 bis boron compounds and then how to selectively get stereo control and transmethylation. And this is an example based on some computational work with his colleague Muki Baik. They proposed that the reaction proceeds through this open transition state. There's some really cool mechanistic experiments if anyone really is curious about taking a mechanistic deep dive that even involves doing isotopic labeling. So going in with a mono labeled 1,1 bis boron compound and then seeing which of the two centers actually undergoes transmetallation.
Erie?
Yes.
In that transition state, is that lithium bound to the oxygen of the B-net?
Yes.
Okay.
Yeah, this is a transition state you wouldn't necessarily predict a priori. The bridging lithium and the extra bridging alkoxides are what fell out of the computation as the lowest energy pathway. Okay, in terms of relative transmetallation rates, let's consider an organotin series. And here again, I think this is probably in line with your intuition about how these reactions go, which is that SP hybridized carbogenic groups transmetallate faster, and then next fastest is SP 2. Alkenyl are faster than aryl, and then the slowest are alkyl. And so this, I think maybe an experiment that you've done is to take something like a tributyl aryl tin reagent and run that in a Stille coupling, and only the aryl group gets transferred, not the alkyl groups typically. So that is reflected in these underlying trends. And there is an effect with these SP and SP2 hybridized coupling partners that they can they benefit from pre-association between the filled pi bonding orbital and the metal that is being transferred to. And so I've illustrated that in the case of this diaphene. So that would be just to make that crystal clear. Oops, I actually need to move this down. Okay, last one to cover are organoborons. And this is interesting, I think, for me, because we'd think that 50 years since the discovery of the Suzuki coupling and having the reaction run millions of times around the world, we'd know everything there is to know about it. It turns out that one of the constituent elementary steps until very recently actually was more or less a black box, and that's this transmetallation step. And this had been highlighted in a number of reviews that no one really had good evidence for how this key step took place. And there was a seminal report from 2016 from Scott Denmark's group that I think really provided a clear roadmap for what's going on here. And the key discovery in this paper was characterization, unambiguous characterization for the first time of this so-called PDOB, which I have highlighted in pink here, intermediate. Again, this type of thing had been proposed before, but proposing it and actually having evidence for it are two different things. And the Denmark group found that you could get at this intermediate by two different routes, either by taking an oxidative addition complex and then treating it with a boron 8 complex, where boron is anionic and activated by coordination of a hydroxyl group, or alternatively preforming a palladium hydroxide and then transmetallating with a neutral boron. So these PDOB intermediates could be characterized. I think he has in this paper 3 different flavors and with different levels of bridging and whatnot. One of those I've highlighted the structure of here in this gray box. And then what needs to happen from this intermediate is you lose one of the L-type ligands, the one here highlighted in green. And then you can imagine now you have a free coordination site for the aryl group to swing on, and you get a 4-membered transition state, 1, 2, 3, 4, where the aryl group's transferred. Loss of boric acid or deprotonated boric acid to now make the trans, and again, we'll come back to these sequences and cross-coupling. Now the trans diaryl palladium species, which needs to undergo trans to cis isomerization prior to reductive elimination. And actually, in some ways, even though it's really just my own ability, my own slowness in getting through my notes, we're fortunate that I didn't get to this last week, because in the days since the last lecture, there was actually a really interesting report from the December and colleagues, where they were actually able to characterize a model complex by X-ray crystallography for the first time that shows this similar PDOB connectivity. And the key trick that they played was to connect the supporting ligand and the aryl group of the boron. So it makes it a bad transmetallating agent, but it makes it sufficiently long-lived to be able to get single crystal X-ray. So we can send that out as an attachment in case anybody's interested. But part of the point of highlighting that is just to show that really this remains actually a hot topic of mechanistic investigation in the cross-coupling literature. Okay, so let's go ahead and wrap things up then by here with problem of the day number 4. Let me reshare the screen. So this question asks you to consider a cross-coupling here. I think this is from the Byers group. Is that, Van maybe can nod if I have that right? Okay, she's nodding. Iron catalyzed Suzuki type cross-coupling, alkyl aryl coupling. And they have this observation that this reaction does not work with without the lithium amide base. So what's going on here? Could you provide one explanation or 2 explanations that would be consistent with this? Feng, what do you think?
I think one explanation for this should be that the amine base used to coordinate with the B-pin, so make the B-pin like a BOH3K as you draw above.
Okay, and what about, do you have any other explanation?
The second, which is I think less possible, is the amide is used to coordinate with the iron, so to promote the reaction to happen.
Okay. Why do you think that one is less likely?
It's less likely because I think the first one is more likely to be the reasonable one because mechanism you draw.
Okay. Yeah, I think I can't remember. I don't think they have unambiguous data supporting one or the other. Both are plausible explanations. So this is a key theme. We saw this above, but I did want to highlight this explicitly, that when you coordinate an anionic ligand to boron and make this 8 complex, then there are several benefits. One is the ability then to pre-associate and to the metal and transfer. The other is that now you start to accumulate delta minus character on the carbogenic group that's being transferred. So an 8 complex is a more nucleophilic form of the carbogenic group. That I got so excited I didn't draw the X. And then the other possibility was Fung, that you proposed smartly, was in direct analogy to the palladium hydroxide complex that I showed above, and recognition that that's an alternative activation mode. And I think both have been proposed and depending on the system of interest as being operative. Good. Any questions on this? Okay, so let's now jump into a discussion of carbenes. I'll first ground this discussion with stuff that you already know and should already be familiar, which is just reflecting back on what we already know about carbenes, not including the metal. So the overall structure of a carbene is shown here on the left. So you have 3 sp2 hybridized orbitals in plane, 2 bonding, and then one which can, depending on the electronic configuration, can be a lone pair. Maybe I shouldn't draw it that way. Along with one p orbital that is orthogonal to the plane. And then 2 possible electronic configurations, 2 flavors of carbene, either a singlet, where the sp2 hybridized orbital that's in plane with the carbogenic groups, or I guess they don't have to be carbogenic groups, but the R1 and R2 groups is doubly occupied, and then a triplet configuration where that orbital is singly occupied, and then the p orbital is singly occupied. And then one of the twists here compared to the other ligands that we've covered so far is that carbenes in general are with only very rare exception, are not stable in their free state. So when we think of, our typical workflow for things like electron counting, where bring the ligand back to its closed octet, to its stable form. And that same sort of thinking does not necessarily apply to carbenes. So we need a somewhat of a different workflow. And it's also a relatively new area of study. The first reports of any type of carbene only appeared, 60-ish years ago. So in the course of, in the context of all chemical research, it's a pretty young area of study. And again, I think the theme here is one where you see researchers saw bizarre complexes with bizarre structures they don't understand, and then worked hard to try to unpack what's going on in terms of structure, bonding, reactivity. So this is kind of like a very brief 1-minute overview of a lot of different types of metal carbenes that we'll see, and then we'll unpack the ones that are important. So if I go through this quickly, it's just because we're going to see these same things later anyway. And so this is organized in parallel to how the introduction of this chapter in the Hartwig textbook is presented. But there are several major categories of carbenes, but really the 2 that are most I think central for thinking about structure and bonding reactivity are those shown on the left here, which is the Fischer type and the Schrock type. And this really defines two different extremes along a continuum of metal carbene properties and defines two different systems for electron counting, as we will see. So let's first consider the Fischer type. Often Fischer type carbenes are bear heteroatoms directly attached to the carbene carbon. The metals involved are typically middle to late transition metals and typically in low oxidation state. And we'll talk about the ligand sets that are compatible with that. The other type is the opposite end of the periodic table and the opposite trends, which are Schrock type carbenes. These are typically high valent, high oxidation state and early to middle metals, early to mid metals. And then the way in which the carbon metal bond is polarized is different between these two systems. So the Fischer type, people like to think of these as being carbonyl-like. The metal carbon bond is polarized like a carbonyl, such that the carbon atom is electrophilic and the metal is nucleophilic. And then the Schrock type is the opposite. It's more organometallic like. Maybe that's not actually descriptive. Let's say more like Grignard like. And then there are three other types of metal carbenes here. In terms of electron counting, all of these would fall into the general Fischer category. And I'll come back to this explicitly later, but there's carbenoids, and these we have, maybe some of you have already encountered these in chemistry you've done. Carbenoid, that terminology just refers to a organometallic species where the overall reactivity of the species parallels free carbene. And it's not really clear what the nature of the bonding situation is. That's sort of the historical origin of it. So things that are carbenoid, they react like carbenes. They do things like insert into CH bonds, cyclopropionate alkenes, etc. And the canonical examples of carbenoid reactivities are things like dirhodium tetracarboxylates and reactions like CH insertion, cyclopropionation, as I said. So signaling elements that you're in a carbenoid regime are seeing a diazo starting material. These types of compounds are often derived from diazos. And then a dirhodium complex, or there are other other types of complex that do these are like copper complexes bearing NN ligands, for example, ruthenium tetraamine ligands, or ruthenium porphyrin complexes, for example. Another type of carbene are vinylidines. These are most often made from a metal, typically a late metal, plus the corresponding terminal alkyne. And there's a transposition of the terminal CH from the alkyne to so I'll let you think about how that transposition takes place. And vinylidines, there's the singlet form of the vinylidine in the absence of any metal, singlet form of vinylidine is much more stable than triplet form. And so as a result, most vinylidines are Fischer type. That's ugly. And then there are N-heterocyclic carbines, which we can discuss more detail. These are typically spectator ligands and share a lot in common with more archetypal Fischer type carbines. Okay, so let's consider. Sorry, let me zoom out. So let's now consider these three, which I think are maybe the most relevant to things that we'll encounter later. Each of them one at a time. So Fischer Carbines, as we said, so this is the first Fischer Carbene. Here, a chromium pentacarbonyl complex. We'll talk about how it's made. And then the bonding situation is such that the carbene is coordinating as a singlet with this sp2 hybridized lone pair serving as a donor, and then a filled orbital on the metal serving engaging in pi back bonding. And then the stabilization that comes from having these heteroatom substituents is that the lone pairs from those heteroatoms can further donate into this, quasi unoccupied orbital of p hybridization on the metal, or of p symmetry on the metal. And so, as we said, these are carbonyl-like. So nucleophilic attack is favored at the carbon atom. Electrophilic attack is favored at the metal atom. Just an analogy to how like Lewis acid activation of carbonyl compounds. In terms of electronic configuration, very commonly you see these as 18 electron complexes, D6, again, late transition metals, and then in low oxidation state. The metal here is typically stabilized by pi accepting ligands. We see in this case pentacarbonyl, because it's an electron rich metal, you need pi accepting ligands on the metal. And then we talked about the benefit of heteroatom stabilization, and we'll see how this contrasts to Schrock type carbines. You can also get some degree of stabilization in the Fischer case from aryl groups or vinyl groups, which similarly, because they have these filled pi bonding orbitals, can donate electron density. And then there's a difference actually in bond strength between Fischer type and Schrock type carbines. Fischer type are typically weaker, and that manifests in terms of the metal C bond distance, which can be read out by X-ray crystallography, and we'll cover some specific examples of that. And then in terms of electron counting, the key point here is to remember, and I hope this is at least somewhat clear from the bonding depiction here, that these are L-type ligands. They coordinate as a sigma. I mean, you can think of them as coordinating as a sigma donor, and then just engaging in pi back bonding from the metal. So then the Schrock type carbines, I mean, we go through point by point quickly, but basically everything you just heard, the opposite is true of Schrock type carbines. So they're nucleophilic at carbon and electrophilic at the metal. The carbene is best depicted as being in triplet state. So you have a singly occupied sp hybridized lobe engaging with a singly occupied d orbital of appropriate symmetry on the metal, and then likewise a filled p orbital on the carbene engaging with a singly occupied d orbital on the metal of different symmetry. And really, what this boils down to, I mean, this is, we'll see that this really gets down to sort of like inventory of where you define an electron being on a metal or on the ligand, and sometimes there's a breakdown in this framework. But anyway, this is first you kind of have to learn the general rules. So these are the general rules. So these are most commonly 14 or 16 electron complexes. They tend to be quite reactive with anything they can find for the most part. Typically D0, D2, early transition metals like tantalum, we'll see examples of titanium, etc. Those metals are typically in high oxidation state, and then as a consequence, they're the type of metal centers that are stabilized by very strong sigma donor ligands that don't have a lot of pi accepting character, like alkyl ligands or CP ligands, for example. And then these ligands are the Schrock type carbenes most commonly just have an alkyl group or one or more alkyl or H groups hanging off of them. They very rarely have anything other than that, and typically not heteroatoms. And you can imagine why that would be destabilizing if you thought about that R1 group, for example, pumping electron density into what's already a partially filled orbital. And then, as I said, Schrock type carbenes have strong carbon metal bonds that have more double bond character. And then in terms of electron counting, these count as X2 ligands. I kind of think of these as like two alkyl ligands that just happen to be co-localized, like a methyl group times 2 that's just the same ligand, and that's helps me think about the underlying reactivity and being sort of Grignard-like in a way, and then also in terms of how I do the electron counting. If that mnemonic is not useful to you, then just pretend I didn't say it. And then NHCs, we'll cover this in a little bit more detail actually when we talk about ligand properties and parameters and these sort of things. So I'll breeze through this quickly. I've highlighted here just one example of many you could find in the literature these days of NHCs as supporting ancillary ligands. This is an example from the Organ group, these Pepsi palladium precatalysts for cross coupling, but there are many that I could have picked here. Generally, the carbene, the NHC in this case is a spectator. It acts analogously to a phosphine, both in terms of what role it's playing and in terms of electron counting. And the Crabtree textbook, Crabtree adds a lot of color to his discussion of the science, and he describes these in the textbook as Fischer Carbines on steroids. And I like that because it gets at a number of things, like the fact that there are two heteroatoms, both now pumping in electron density into the carbene. It also kind of defines, the electron counting of these as being Fischer type. And so to me, that's something that's easy to remember. So these are strong, in comparison to phosphines, they're stronger sigma donors even, and their pi accepting ability has been the subject of debate, but in general, they're considered to be weaker pi acceptors. And this area of study lied pretty much completely dormant until, let's say, the early 2000s. And it was really spurred by the development of these, stable carbenes of this type here. by the Arduengo lab, and this built on previous contributions by Wanslick. So sometimes these families of carbines are called Arduengo carbines or Wanslick carbines, and they were doing this work not necessarily in the context of organometallic chemistry, but just this trying to chase this fundamental challenge of, is it possible to make an isolable, stable, monomeric carbene? And the first successful one is the one shown here, where you have two atom mantle groups off of nitrogen and then unsaturation on the backbone. These are singlet. This specific example from Arduengo is a singlet carbene, and that's evident from the angle, the NCN angle of 102 degrees, which can be read out of the crystal structure. And so, like now that researchers had carbines that they could create in stable form, and then they became more interested in ligating them to metals. And I think the first really successful example that caught people's imagination was the second generation Grubbs catalyst, and then the rest, as they say, is history. A few other details.
Oh, sorry.
Yes.
Can I ask a clarifying question? So
Yes.
these are, if they're Fischer Carbene on steroid, but Fischer Carbines are stabilized by strong pi accepting ligands, I think I'm missing, like, if these are weak pi acceptors, what makes them Fischer-like?
Yeah, so maybe that point was a little bit unclear. When I was talking about pi accepting ligands, I was referring to the non-carbene ligands.
Oh, okay. Got it.
So in this case, let's consider this archetypal case. The COs are strong pi acceptors. Those are not part of the carbene system.
Okay.
Yeah. So I was talking about the other supporting ligands. Okay, thanks, Kelly. It's a good question. Any other questions? Okay, now let's go through some synthesis and reactivity. So the first Fischer type carbene, and this is still to this day, I think, the most common way to make these. Was done by addition of methyl lithium or any alkyl lithium, as you can imagine, to Tanner's favorite complex. I don't know if it's your favorite, but maybe the complex he's used most, tungsten hexacarbonyl. Sorry, I'm making a mess of this. Which, so you can draw that addition. Now the most reactive, methyl lithium is a strong nucleophile. So the most electrophilic site on molybdenum hexacarbonyl is one of the carbonyl carbon atoms. So it adds in. There's two resonance forms that you can think about. The one shown on top, and then this other shown here. Then react with strong methyl electrophile to cap the oxygen of this metalloenolate, if you want to think of it in those terms. And then likewise, you can add other, they don't have to be carbon-based nucleophiles. You can add heteroatom-based nucleophiles. So LDA, for example, can add similarly to a carbonyl of, in this case, chromium hexacarbonyl and then cap with an electrophilic alkyl group. And here I had made this point that the metal carbon bonds in Fischer carbines are relatively weak, and so that's corroborated by the X-ray crystal structure, where this bond is found to be 2.13 angstroms, and a typical chromium carbon single bond is only on the order of 2 to 2.2 angstroms. So it's very single bond like, and we'll see how this contrasts to the Schrock case. And then I've drawn, for this particular example, the two resonance contributors that can give you a sense of both structure and reactivity. Okay, so let's queue up the poll, Van. So I've said that okay, let me share POD number 1. So I've said that Fischer carbines are ester-like, and now we want to test, I guess, either your knowledge, or if you haven't seen this before, your intuition. So we have 3 metal carbines, and we're asking the pKa of the alpha CH bond and how that compares to a simple ester, in this case, just methyl acetate, and to order these in terms of increasing pKa. So which is the most acidic CH bond, which is the least acidic CH bond. So take 30 seconds to make your answer, and then we'll go through. Okay, I think we have about half the people. So if you don't know, please guess. Okay, Van, do you want to wrap up the poll? Okay, we've got quite a diversity of opinions, but the plurality of votes is B, then A, then C. So C would have the highest pKa, then A, then B. And I think that is indeed correct. So I guess first and foremost, the thing that should be going through your mind is that C, we've talked about how the carbines at the carbon of a Schrock type carbene are very anionic in character, very nucleophilic. So to deprotonate directly next door is going to not be favorable. So that one, I think, you should be thinking that that's going to be the highest pKa. And then the other two, you might debate as to whether it's A or whether it's B. And I think a lot of people were having that debate. You see 4 people have answered that way, or the other way of the plurality. Okay, so let's go to actually take a look at some numbers here. So you can take a look at the right of my screen here. So comparing the alpha proton acidity, it's about 8 to 12 in the case of Fischer carbines, whereas from our Evans pKa table at Bordwell pKa table, we know that these are 25 in the case of esters, and then amides, of course, are less acidic, and the amide equivalent of a Fischer carbine is also less acidic. So now let's unpack this ester-like reactivity with some examples. So treating a Fischer carbine with in amine, and just like with an ester in the presence of an acid or base catalyst, you can get exchange of that heteroatom substituent for the amine, or likewise with an alcohol. So let's now put to practice some of these general principles. I'll call on a couple volunteers for this. Okay, Camille, do you want to walk us through this first sequence?
Can you scroll up for a sec? I didn't get to look at the left side.
Okay.
Okay, thank you. Yeah, so I guess you would replace the OR with
so yeah, previously, this might be a little confusing. Previously, I had shown that LDA can exchange for OR, but in the presence of an acidic alpha proton, probably the fastest thing that's going to happen is that LDA is not going to, which, you know, LDA is a hindered base, is not going to act as a nucleophile.
okay, so then it'll act as a base and you'll deprotonate alpha.
Okay.
And then I guess in the presence of an electrophile, you'll just trap that with the electrophile.
Beautiful. Okay, and now in this somewhat more taxing example where the electrophile is an ethylene oxide, what would you expect to happen?
Sorry, is that what's ethylene oxide? That's the, okay. I guess you just open the epoxide.
Okay, so you're thinking like this?
Yes.
Okay, I like that. So 2 carbons and then O minus.
And then I guess if it's electrophilic, you could form a ring.
Beautiful. So now this is gonna swing back down and you get a metallolactone. And then what about this last step? Camille, any thoughts here? DMDO or some other strong oxidant, like I've drawn the cerium 4.
An oxidant. I mean, I'm guessing the ligand will fall off.
Okay.
I don't know.
Let me draw this in a suggestive way. Let's see if I can take advantage of the rotation.
Oh, so you'll add across the double bond.
Beautiful. So here you would get out the, if you want to think of it that way, this will actually convert your metallolactone to a lactone and the corresponding chromium oxide compound, I guess, ultimately. Super, Camille. Any questions on that?
So is it turning over or no?
This is not turning over. And this you will see as a theme with Fischer Carbines is that the reactivity is very cool and interesting, and they generally have been hard to turn over. Okay, let's consider one more example here. Fischer Carbene plus alkene, and the particular type of alkene we're focusing on are of the Michael acceptor type, so activated alkenes. These can engage in 2+2 type cycloaddition to make a metallocyclobutane. This is setting the stage for what we'll cover later in olefin metathesis. I should note that because this is as drawn here, I haven't defined the metal, but you know, I'm implying this is an 18 electron complex, but so the first step needs to be ligand loss to associate the alkene, then 2+2, and then well, I've given it away with the title here, so I'll just draw the product, which is CC reductive elimination. And when I say that, I'm talking about this C and this C reductively eliminating to give a cyclopropane. And then recapture of the metal with that freed ligand.
I have a question about the regiochemistry of the 2+2.
Yes.
So I guess the carbene, carbon, because it's electrophilic and the metal is nucleophilic, I would have thought that the opposite regiochemistry will predominate, considering that you have a alpha beta unsaturated system, like electron withdrawing. So like you'd have a delta plus at the beta position, delta minus at the alpha position.
Yeah, it's a good question, Noor. I may have this backwards in my notes. I can double check that. The product in either case will be the same because of it's a symmetrical cyclopropane. So I can double check that. I think what you're saying intuitively seems right. So basically, we're just matching the partial plus and minus, right? Okay, let's jump over to problem of the day number 2. And to do this, we'll boot you into breakout rooms for a brief 2 or 3 minute discussion. Let me queue up the problem. This one is for the total synthesis folks out there, an actual application of Fischer Carbene towards the total synthesis of kendamycin. So you have the alkyne on the left, Fischer Carbene, simple reaction conditions, THF, slightly elevated temperature, and then we get a new product, A. So what's that product? And then what is the mechanism? Okay, Kelly, what did your group come up with in terms of product and in terms of mechanism? I will say that as a caveat, the mechanistic details of this transformation remain debated. So we can draw some reasonable structures and then we'll have to live with that uncertainty. But what did you think in terms of product here?
So first we had dissociation of one carbon monoxide ligand.
Okay.
By,
I'm not going to draw all this out because it will just be hard for me to keep up. But okay, go ahead. What's the CO then?
2+2 with the alkyne.
Okay.
Between the chromium bond, and then I guess we drew out an elimination to give you the cyclopropene, but weren't quite sure where to go after that.
Okay. Anyone else want to chime in? Consulting from the audience here?
So my group just talked about something different. We talked about doing a 4+2.
Okay.
To
To
so
give
getting
us
a larger metallic.
cyclopentina. Oh, 4+2 to get a metallocyclohexene, and then some.
And then
what would happen from there?
We suggested reductive elimination with like CO insertion, so you end up with a cyclohexadienone.
Okay, I like that in terms of product. Anyone else want to chime in? Get anything different?
We talked about doing a 2+2 with between the alkyne and the carbene first, followed by a retro 2+2 to give a new carbene.
Okay.
Which after CO insertion, you generate a ketene.
Okay.
And the ketene can do electrocyclization.
Aha. Okay. And what is the final product, Nathan?
It's the phenol, a phenol.
Wow, nailed it. Okay. Has your team seen this before?
I think we've seen this in MOS maybe.
Okay. Hopefully I have the regiochemistry right. So this is overall a 3 + 2 + 1. The 1 is CO. I've tried to highlight the components here, and CO goes adjacent to the largest group. I think every team had some of what was part of the way there, which was cool to see. And this, I kind of think of it, I don't know, people might not like this. I kind of think of it as like a 6-membered analog to a Poisson-Kond. And this is a name reaction. Brendan, I guess I should ask you if you know the name reaction.
Yeah, I should have recognized this, but Phil sent me a frantic email asking me where I was, so I got kind of sidetracked. But this is a Wolff-Dots reaction.
Okay. And or just referred to as the Dutz reaction. And Wolff, I think, is Brendan's undergraduate supervisor. Is that right? Same Wolff?
Yep, same guy.
Okay. And so the mechanism, again, details remain debated, but I think Nathan was most of the way there. So first step is, I guess I should just draw these as, yeah, first step is probably loss of CO2, as Kelly said. Then coordination of the alkyne, 2+2, retro 2+2. Addition of carbenes across alkynes. I kind of always draw in this way. If people have attended boot camp, you've maybe already seen this, where you add this group to one carbon, and then this group to the other carbon. So it's R. So that's the product of a 2+2, retro 2+2 across an alkyne. And then insertion of CO to spit out a ketene, and the nature of that ketene, you can debate whether it's as drawn or whether it's a oxymetallocyclopropane, I guess would be another formulation. And then it's believed that the 6-pi electrocyclization is not involving the metal. Okay, good. Any questions?
I think the product is the OH in the green.
Thank you, Anne. I think I copied it from the paper, and they have a methylation step. And this is one of Van's favorite reactions. So since she's TAing, I wanted to make sure we covered it. Okay, we'll stop things there. Sorry, a couple minutes over. Just a few quick things to wrap up the discussion of the Schrock type next time, and then we'll be on our way with catalysis. Okay, thanks everybody.